I always like to start, like you guys know, with kind of a funny image or a cartoon that represents a catastrophic design failure, or something that just evokes the engineer who designed the thing not really thinking about the end user. And this is a great example from my childhood. This actually happened when I was in elementary school. So, President Reagan, Nancy Reagan, war on drugs. And so the federal government, you know, paid to have manufactured millions of these pencils, right? You guys hopefully recognize these yellow things as pencils. I don't know that anybody uses these types of pencils anymore. But this was, what we used in elementary school in the 70s and 80s, 1970s and 1980s, not the 1870s or 1880s. I'm old, but I'm not that old. And so the way that this works is it's meant to just be a slogan, right? Which is one of the war on drugs slogans that the federal government was pushing at the time, right? Which is too cool to do drugs. And so you'd get a pencil and it would say too cool to do drugs, and you would feel compelled by that slogan to not do drugs, I guess was the goal. But what happened? Well, these pencils, the way that they get sharpened is you stick up the pencil into a pencil sharpener, and it takes away some of the material to reveal the lead point and the sharp tip that you can continue to write with. And so kids realized very quickly that you could take these pencils and you could start shaving them down in a pencil sharpener, and you could change the message, right? So it went from too cool to do drugs, which was the original intention, to cool to do drugs, which is not good, and then do drugs, which is even worse, right? And then just drugs. And so, like, the coolest thing when I was, in third grade was for kids to grab the too cool to do drugs pencils out of the, federal anti-drug program pencil bin that everybody had in their classrooms, and just stick them in the pencil sharpener and grind them all the way down until they just said drugs on them. And so these kids were basically walking around with, like, federally funded pencils with the word drugs and like embossed on them. And it was bad in two ways, because one, the pencil says drugs, which is bad. But then the other thing is, if you guys have ever tried to write with this tiny short little pencil, it's really hard to write with a short pencil. And that was the cool thing, right? Was to have the short pencil that said drugs on it. And so everybody would, like, intentionally drill their pencils down to the point where they said drugs. And then people's handwriting sort of fell off a cliff because nobody could write well with these short, stubby little pencils that said drugs. Yet everybody wanted one. And so this was actually like a double design failure, right? The people who designed the pencils not thinking about the end user, because one, they hadn't thought about what would happen to the message when the pencil got shaved down, which was funny in and of itself. But then also, this final version of the pencil with the word drugs on it became the most popular version of this particular product, and it actually hampered students' ability to write well with the pencil. So both, the wrong message was getting sent out, and students' handwriting was suffering as a result of these federal too cool to do drugs pencils circulated all around the country. So anyway, I remember this was kind of an awesome moment of, like, major design fail in my childhood. So anyway, so just wanted to share that story with you guys as another example of the designer not thinking about the customer, the end user, and how the product would actually be used or received by the people ultimately using it. So anyway, so let's hop back into dynamics. And this was a struggle for me, because there's not a lot of moving parts here. In some of our other RER artifacts, we've had parts that twist and move in a linear fashion at the same time. So that was sort of obvious to do, translation theorem type analysis on those. Or we've had other parts where there was, a really obvious, like, rotation against friction. And so you could, like, look at the spin down or the spin up of whatever it was, versus time as a function of friction. So like rotational, velocity type things. But this one is pretty tough because you really can't, at least, from being remote and not being able to get into the inside of the fan, pretty hard to sort of get a sense of anything that's going on inside of the fan in terms of the dynamics. And so at the end of the day, you've basically just got a fan with a DC motor attached to it, spinning at constant velocity, more or less. And that's it, right? So there's not a whole lot going on in terms of dynamics. So maybe in the real world you might not even do a dynamics analysis, but then I started thinking about, well, wait a minute. This fan is spinning, and I just finished the Mech 1 analysis, right, where I figured out that there's some mass that you can stick at the end of one of the fins, and if that mass gets big enough, you can actually cause a vibration that forces those fins to fail sooner than the manufacturer specified failure life for the entire product. And so I was thinking a lot about like vibrations and cyclic loading and these fins. And I thought, well, my God, what if the fins have a natural frequency that is accessible by the fan, right? You put 12 volts on the fan, you get it to spin up to, I think Devanji measured, she's one of the ULAs, if you guys haven't interacted with her yet. She measured, I think, something like 5,500 RPMs. And so, wow, if you're a fin with a natural frequency somewhere in that range, you could imagine a situation where this fan, this fan, FAN, is actually spinning and exciting a natural frequency, right? Or a harmonic of a natural frequency in the heatsink and causing basically an amplification of a vibration that we already know from the Mech 1 analysis could reduce the lifetime of the overall product. And so that's kind of what I was thinking in terms of a dynamics analysis. And I realized this sort of skirts the edge between dynamics and vibrations. And vibrations is not a prerequisite, so I get that, and I'm sorry. But I think having gone through dynamics, you guys know about harmonic oscillators in the equation of motion. And so, like, for example, a spring mass damper system, and you guys know how to find like natural frequencies of spring mass damper systems and from your dynamics experience. And so I thought this is probably fair game to walk through how you would calculate the natural frequency, assuming that one of those fins is acting like a spring. So that's what I endeavored to do. And let me just pause here quickly and mention, so I said before, like, I don't identify myself as a dynamics guy, but I grabbed this list from Jonathan Brooks. So this is the list of, I should say, Jonathan Brooks's dynamics techniques that all MAEs should know. But Dr. Brooks gave me this list of all of the things that he thinks MAE students should know, having completed a undergraduate dynamics course. So we've got scalar and vector algebra, we've got kinetics of particles, kinetics of systems of particles, and kinetics of rigid bodies, right? So here's like Euler's law of motion, and so forth. And I think so to compensate, right? This is that whole, like, if you're not good at something, you compensate by giving like a whole lot of it to people who are asking for it. So to compensate for me not necessarily being a dynamics guy, the dynamics section of the Canvas site, I think, has like the entire, let me see if I can find it here. The entire, I'll pull this up. See, this is the beauty of using two screens. Let's see, view all pages. Let's see if we can find dynamics. There it is, dynamics review material. So, so talking about overcompensation, right? Like, it's basically the entire dynamics class, like, on there for you guys to review if you feel like you need to. So all this stuff is on there. These are all lecture notes. There's, of course, the textbook. And then there's a number of lectures that I have given from before, from previous RERs, to show you the analyses of how those work. So that's all up there for you guys to review. Um, anyway, so trying to kind of put the RER dynamics analysis into a box that will hopefully make sense to you guys. I figure I'm gonna talk about the fan heatsink system basically as a harmonic oscillator. So that's where I'm going with this. To try to find, as we'll see in a second, the natural frequency of those fins, and to see if the rotation of the fan excites those fins at a natural frequency or a harmonic of a natural frequency, which of course is bad, right? Because that now amplifies the vibration and could potentially reduce the life by cyclic loading of these. I think now we're pretty convinced that they're aluminum fins on this heatsink. So not being, a hardcore dynamics guy, I had to simplify this for myself. And so here's my approach, right? So recognizing full well that the fan is mounted on, you can see it here, mounted in 4 unique places, 1, 2, 3, 4. And each one of those unique mountings is one of these pitchfork shaped fins, and it's actually the thicker, right? This is an outer fin that I'm pointing at here. So this one is a thinner one, and then there's a thicker one that's inside here. Let's see if we can see. Yeah, okay, this is a better view of it. There's a thicker one that's inside here, and that's actually where the fan is mounted times 4, right? So okay, but that's a not so fun problem, right? To try to figure out what's going on with 4 different mounting points. And so again, just trying to make this easy on myself, I'm going to take a bounding approach, and if this bounding approach works out, we'll see ultimately that it doesn't, sadly, but if it works out, I've just saved myself a whole bunch of trouble. So I'm going to say that I know that the fan is heatsink mounted at 4 spots. It's definitely harder to find the natural frequency with 4 mounting points than it is with 1. But I know that the natural frequency goes as the square root of K, right? Because the natural frequency, you guys, I think, should remember this from harmonic oscillators in your dynamics course. The natural frequency of an oscillator should go as the square root of K over M. K is the spring constant, and M is the mass of the system, right? So if you just have a spring mass all by itself and it's oscillating back and forth, that's the frequency that it oscillates with, is square root of K over M. So knowing that force goes as the square root of K, I think I'm right in saying that 1 mounting spot is always going to be less stiff than 4, right? So if I have 4 of these fins, the K value is definitely going to be higher. The spring constant is going to be higher than if I have 1 of these fins, right? Because there's 4 of them, and there's 4 times the thickness. So it takes 4 times the force to get more or less 4 times the force to get the same displacement. So 1 mounting spot is always less stiff than 4 mounting spots. And so the logic goes, if I find the natural frequency for 1 mounting spot and compare that to the maximum fan frequency, if that natural frequency turns out to be higher than the highest fan frequency, like the highest rate that the fan spins, then I'm never going to hit a natural frequency point, right? Because the system is only going to get stiffer as I add additional connections, additional mounting points. And so this is a bounding approach, right? So this is bounding, right? It's what you do when you don't know what to do, right? It's either this or Buckingham Pie. So I'm going to bound the system by just saying that I've got 1 mounting spot instead of 4, and hope that the frequency that I get is much higher than the natural frequency that I get is much higher than the rotational frequency of the fan. And if that's true, then adding extra mounting points makes that sort of spring that's holding the fan even stiffer, and I'm never going to hit that natural frequency, and therefore never going to have this vibration amplification. So that's my plan, my approach. So let me just pause there because that's sort of weird and kind of roundabout thinking perhaps, and just ask if anyone has questions about what I'm trying to do. Nope. Good so far. Okay. All right. Okay. Cool. So there's a couple of different ways that I thought of to try to do this. And well, the first is to just run an experiment, right? So to actually measure the spring constant of one of these pitchfork shaped fins, and go back to my natural frequency equals k square root of k over m, and just be done. And that's fine if you're me and you have access to the shop and the resources to do that experiment, which I do, and I'll show you the results here in a little bit. But if you don't have access to those resources, then I think there's two other ways to get at it. So one is to just imagine that this fin is, at least at sort of first approximation, just a massless cantilever supporting some force F at its endpoint, right? It's not quite that. Yeah, okay, there's this pitchfork shape in here, and that mass isn't, or the mass of the fin, might not be quite supported directly at the end, because you've got kind of the screw that's going in and distributing that mass over a little bit of a distance. But at least as an approximation, right? This is probably a good first cut at it, right? Plus, this isn't rocket science, right? It's if we're way far away, like an order of magnitude away from the natural frequency, compared to the fan rotation rate, then it doesn't matter if we make some assumptions and we're off by a little bit. So that's kind of the first approach. And so the way that I would tackle that one is, E is a material property. I'm pretty sure we've settled on this stuff being this heat sink being made out of aluminum. I is the moment of inertia for the cantilever shape, which I would just take it as a rectangle cross section and find I. L is the total length of the cantilever from the base all the way out to the tip, and then F is the force. You might use the force based on the entire weight of the fan as one possibility. You might also cut the force into a quarter, because maybe you want to be a little bit more sophisticated, and that there's 4 mounting points, and so each one of those mounting points more or less is going to take on a quarter of the total weight. So plug in those values and get a natural frequency and compare. So that's kind of, I think, that the simplest analytical approach that you could take and get a number that you could at least argue is in the ballpark. There's a slightly more sophisticated version of that equation, and I don't actually know how much these two differ, probably not by a whole lot. But this one is for a uniform cantilever with weight W, supporting an end force, which is force F. So it's basically this over again, except now I'm taking into account the mass of the cantilever itself in my overall calculation, right? So whereas before the cantilever was just sort of this magical massless, one-dimensional, or I guess two-dimensional line just sort of floating out in space, now it has some mass associated with it. And again, I don't know if that's going to matter or not. So you got to sort of put in the numbers and see. Even interestingly, even that in and of itself would be kind of a neat analysis that you could do, right? Because it's pretty easy to see that this equation, which is the natural frequency equation for uniform cantilever with some weight supporting an N force F, it collapses to this equation if that weight, so here's that weight W, which is the weight of the cantilever beam itself, goes to zero, right? If it goes to zero, this term goes away. And then this just becomes, EI, let's see, EIG. Oh, yeah. Okay. So the one thing that's different is what is this G? We're actually going to talk about this a little bit later. So that's gravity. And this force has got to be a mass, and this weight has got to be a mass. And up here, I've got the force is actually a force in newtons. So that's the difference, I think, is that this G is sitting there to convert a mass to a weight or a weight to a mass. I got these equations, by the way, from two different sources. So this one comes out of Engineering Toolbox, and then this one, the bottom one, comes out of Rourke's Formulas for Stress and Strain, 7th edition. Which, if you guys don't have a copy of it, definitely get a copy of Rourke's, because Rourke has like everything that you could possibly ever need for how to analyze stress, strain, burst pressure, failure, dynamics, like everything. It's just basically just a catalog of equations for different scenarios that you encounter. So if you own like one engineering textbook, I highly recommend that Rourke be the one that you get, because I'm not a dynamics guy and I've got a copy of it because it's that useful. So just a quick disclaimer that because I'm using two different sources, this F, I'm guessing, is in, we'll have to check the units, is in mass, and this one is in units of newtons, which is force, but I might have that backwards. But anyway, where I was going with this is that this equation collapses into this one if this goes away. And the only difference, of course, is this factor of G. And the reason that I sort of went down the rabbit hole of G is because F divided by G is probably just F here, right? Because one of them is a force, the other one is a mass. And then this 1.732, well, that's just the square root of 3, right? So the square root of 3 is in the square root sign here, and then Rourke just did the square root of 3 and pulled it out as a constant there. So these two are actually just more or less the same equation. It's just this one is modified with the weight of the cantilever. So anyway, okay, so that's kind of how those are related to each other. But that'd be an interesting analysis, just to show that this one collapses into that one for a cantilever of 0 weight. Anyway, so this one is slightly more sophisticated. It does include the weight of the cantilever. Not sure that matters, but it'd be interesting to see how much of the weight of the cantilever impacts the natural frequency as we're solving this problem. So that's worth doing. Anyway, so you guys could also plug in numbers. E is for Young's modulus for aluminum. I, again, is just the moment of inertia, which you can calculate for the shape. Weight, you could, knowing that the material is made out of, we think now, aluminum. In fact, I've even measured its Archimedes volume, so we can get volume divided by mass to get a density, right? So you wouldn't even have to look up a density. You can get it exactly here to put in a weight for just the cantilever itself. So anyway, the point is you can plug in all of these different values and actually calculate a natural frequency. So I think you guys could do either number 2 or number 3 with the information that you're given without running, a single additional experiment. But because I've got the toys, I did the first one here, which was to measure the K constant. So here's what I did. We have Bridgeport Mills in the merge lab, and I set up one of our heat sinks on a scale, a balance. So here's the digital balance down here. We had we needed a magnetic surface, which I'll explain here in a second. So we needed a magnetic surface. So here's just a kind of a scrap sheet of magnetic, I think it's steel. Yeah, maybe not because it's rusting, but anyway, magnetic material. And then here's the heat sink sitting on top of the magnetic material on top of the balance. And then this thing coming down is basically a tool that Noel Thomas, our teaching technician, made that attaches to the spindle of the mill. And from, you guys hopefully remember from DML, you can use the quill of the mill to move the spindle sort of up and down in the Z direction. And you can do that with, an awful lot of precision down to, you know, thousandths of an inch, or even tens of thousands of an inch if you're being very careful. And so that's what we did. So we set this whole thing up, and we actually, you can see right here, we bent the two. It's maybe easier to see here. We bent. Nope. Yep. Okay. So we're wanting to get at this fin, right, which is the thicker pitchfork shaped fin, but there's like a non-pitchfork shaped fin in the way, right? So we had to, you can see it here, sort of bend those out of the way so that we can access the thicker pitchfork shaped fin. And so we've got this tool sort of pushing down on the end of the thicker pitchfork shaped fin attached to the spindle of the mill so that we can actuate it in the Z direction with a lot of precision. And we've got this thing here. I've got another image of this. This thing here is a feeler gauge. So it's able to measure the displacement of the end of the fin, right? So you can see this little feeler gauge is sort of sticking out there and touching more or less the end of the fin. It was as close as we could get it without messing things up. So it's measuring the displacement. And so what we're doing then is, I've got a series of images where, and I'm sorry that they're turned sideways, but I guess I could turn them all around, but this is how they came out of my camera, and it's actually easier to read the feeler gauge in this orientation than it is in the other one. So what we're looking at then is two numbers. So one is the displacement of the tip of the thicker pitchfork shaped CPU cooler heatsink fin. So displacement in inches is what the feeler gauge is reading. And then the scale, which is sitting underneath, is reading mass in grams. And that requires a little bit of explanation, but we'll get to that in a second. So just as a quick aside, why did I need this steel sheet? Well, it's because the feeler gauge is attached to the sheet, and the feeler gauge has a magnet on the bottom, which is how it attaches to things, because normally it's attaching to lathes and mills. And so this sheet is sort of superfluous. It's just meant to allow the feeler gauge to attach to the base so that we can, touch off on the end of this fin so that we can measure its displacement. So all of that weighs an awful lot. And so we had to get a pretty beefy scale. But you can see here the scale with all this stuff on it, and the feeler gauge zeroed. The balance, the scale is also tared or zeroed at that point. And so that's our 0 point. And then we just go through a series of displacing by moving the spindle of the mill down by 5,000ths of an inch, which you can see gets read off on the feeler gauge here, and then determining what the force is that gets propagated through the fin, which is now acting as basically a cantilevered spring. So the force that gets propagated through that cantilevered spring onto the scale, which gives us a number. And so I've got a number there, and then I go a little bit further, 10,000ths of an inch, and I've got a number there. I go a little bit further to 15,000ths of an inch, and I've got another number there, and so forth. I do this for a displacement up to 30,000ths of an inch, and voila, out pops my K value. But it does take a little bit of work. So I should mention that I have posted on Canvas. Oh, sorry. Somebody's sent me a quick message here. Okay. Yeah, let me, I'll answer that one at the end, because we're not, yeah. Yeah, that's yeah. Well, I'll answer that one at the end if that's okay. So let's see. Sorry, where was I? Oh yeah, okay. I was talking about I was here. Bing. There we go. Okay, so I've got a K value, but I do need to do a little bit of work um, on the data, the raw data, to extract the K value. And what I've done is put into Canvas um, displacement versus force data just as a series of pictures, right? So you guys just have these pictures, and it's up to you guys to look at the displacement and look at the force and just take that as raw data and kind of work your way through the raw data to extract the K values. But I've got K values, or not K values, I've got data for this thick pitchfork, which is the one that we're doing now, and then also the thinner pitchfork, just in case you need it. So K value for that one you can extract, and then also um, for the non-pitchfork fin, that's the thicker one, and the non-pitchfork fin that's a thinner one. So all four of those different shapes. There's data for. So you could, if you wanted to, go through and potentially find K values for all four of those different shapes, right? Which would be interesting and might be useful to some other analysis that you want to do. So let me just spend a little bit of time kind of talking about how to convert this raw data into a useful K value that's useful for additional analysis, just in case you need it. So the first thing is to recognize that the feeler gauge is measuring in inches, and we probably want not inches, but meters. And so, of course, I've got to convert from inches to meters. And so that's a simple thing that you guys know how to do. But then the other one is a little bit more involved, and this goes all the way back to what I was talking about here, the difference between F and then F and G, which is, this is sort of a weird nuance of scales that measure in metric units. But this scale, which is measuring in kilograms, is not actually measuring a mass, right? It's measuring a weight, which is a force, and it's taking that force and it's converting it through some internal algorithm into a mass so that it can read out in grams. So whenever you talk to, there's old school guys, there's still some of those even in our department, old school guys who are like, oh, like the imperial system is so much better than the metric system, because in the imperial system you have forces and you have masses, and they're two different things, slugs and pounds, right? They're two different things, and there's never any confusion about whether you're talking about a weight or whether you're talking about a mass. And okay, yes, that's true for the old imperial system. That might be a slight advantage, but it's not that hard to convert, right, from newtons to kilograms or kilograms to newtons. You just have to be aware that if you're reading off a scale that's telling you that something has a weight in kilograms, that the scale is using some internal algorithm to take a weight, right, which should have units of force, newtons, and it's converting it into a mass, which has units of kilograms or grams. So we've got to do that conversion, recognizing that the scale is giving us a mass when it's really measuring a force. And so the way to do that is to convert grams to newtons, recognizing that 9.81 meters per second squared is the gravitational acceleration on Earth. And so the force associated with the weight is just equal to the mass, which is what you're actually going for, multiplied by G. So I'm just going to take all of these forces, and I've got force there in air quotes, force in air quotes, and I'm just multiplying by 9. Well, it's actually 0.009.81 because I'm going from grams to newtons, and then I get this guy. So this chart then is, on the x-axis, my displacement now in meters, right? I converted from inches into meters. And then on the y-axis, my force in newtons, because I converted from grams to newtons. And I'm just going to plot that, right? And why do I want to plot that as a line? Well, it's because for a spring, F equals KX. And what I'm really interested in is the slope of this data, right? That's my K value. And so, so there it is, right? So I've got X on the X-axis and I've got F on the Y-axis, and the slope is K. Here's the equation. Y equals some constant times X, the equation of a line, and the R squared value, which is a measure of the goodness of fit. It's probably what I would describe it as. One is ideal, right? One is if all these points lined up exactly. They don't, they deviate a little bit, but this is an experiment and you expect that. But 0.985 is pretty darn good for an experiment. And so I'm pretty confident that, this value is a linear spring constant for this particular fin on the heatsink. And so I'm going to then approximate my K value as, about 7,950 newtons per meter. And the reason that I'm only taking 3 significant digits, I probably should only take 2 significant digits, because I've only got 2, or even in some cases 1 significant digit in my displacement. But I figure I would take 3 significant digits because I have 3 significant digits over here on the force column. So if Shannon Ridgway is watching this, he would probably be upset with me, but that's what I'm doing. So anyway, there's my K value. Now I'm going to take that K value that I just calculated and I'm going to plug it back into my square root of K over M and get the natural frequency. And I struggled with this quite a bit. I'm like, what in the heck is M, right? Because normally in like the world of, dynamics, mass is the mass, like just, stuck on the spring. But in a lot of dynamic systems, the mass and the spring are like the same thing, right? So in dynamics, you sort of idealize everything and separate the spring from the mass. And so I struggled quite a bit. I was thinking to myself, is that mass just the mass of the cantilevered fin by itself, or is it the mass of the fan? So after thinking about it, and you guys might think differently, and if I've got this wrong, please tell me if you guys have a different kind of take on this, but I'm pretty sure that this mass is the mass of the fan, not of the cantilever beam itself. And so we could measure it directly. I destroyed my fan and broke it into a bunch of little pieces and set it on fire to try to get data out of it. So I had to go back to the spreadsheet that DG made and posted up on Canvas that gives you the mass of all the individual components. And so this might be slightly off from the actual measured mass because I took all of her individual components. I added them back together to reconstruct the fan mass, but it's probably somewhere between 22 and 23 grams, which is 0.02232 kilograms. And then plugged into my equation right now. Back to another question about the mass. So this is the value that I put in because that's the total mass of the fan. Because again, I'm imagining that the fan is just hanging off of one fin again to do this bounding calculation that I described in the beginning. However, you might also say, well, the fan is actually the mass of the fan is split between 4 fins, and so you could probably do better by dividing this by 4, this mass by 4, and then taking the natural frequency of a quarter of the total mass of the fan and the housing and so forth. And that's perfectly valid. And if you guys wanted to do that and get a natural frequency based on that calculation, that would make perfect sense to me. But this is the way I did it. So here we are. So I get about 600 hertz, and the units work out. It's a Newton is a kilogram meter per second squared divided by a meter, so it's a kilogram per second squared divided by kilogram gives me 1/second squared. Take the square root, I get 1/second, so hence hertz. So it does actually work out to the right units. So back to the original question: does the fan hit a heat sink natural frequency that causes the vibration to be amplified? We guessed, calculated, right, by at least a bounding analysis that the natural frequency of a single fin supporting the fan is about 600 hertz. And we know from measurements that we've taken in the lab and shared with you guys, that the fan running at 12 volts, which is the normal, I was going to say velocity, the normal voltage that it's supposed to run at, the normal potential that it's supposed to run at 12 volts DC, spins at 5,455 RPMs. So if I take RPMs and I convert that to hertz, it works out to be, provided I've done this right, it works out to be 91 hertz. So that's bad, right? That's really bad, because what I was hoping for is that I would do this whole analysis and I would find that this natural frequency, it was significantly lower than the frequency at which the fan is spinning, right? So the reason that this frequency that the fan is spinning is important is because if there's some slight imbalance, right, like I did for the MEC1 analysis, some slight imbalance, that imbalance basically occurs at this frequency, right? So the heat sink fins that are these sort of now cantilevered springs, as we're imagining them, experience a forcing function that has that frequency associated with it. And so what we wanted was for that frequency to be like way higher. Let's see. Let me see if no, now I've got it backwards. We wanted F1. Yeah. Okay. We wanted. Hang on. Now I've got myself confused. F1. Huh. Why did I write this? Okay. Well, see, this is what happens when you do an analysis off the top of your head without a textbook. So let me try this again. So we got the natural frequency of about 600 hertz. And we took the RPM of the fan and we converted it and got 91 hertz. And what I said here, I think I've actually got this backwards. What I said here is that we sought a natural frequency much higher than the fan frequency, which is what happened, right? Yeah. But that's not actually physically correct. So I think I need to flip this around. So here's my reasoning, and you guys jump in if this is if I've got this wrong. So if the natural frequency, which I just calculated here, is really high, like really high, then we never actually get there, right? The fan spins at a lower frequency than that, and you never get there. But if the reverse is true, if this frequency is low, then the fan can actually spin either through it or at it, and that causes badness. Yeah. Okay. So, hey, this is great news, because I got my little Macaulay Culkin Home Alone here saying, oh no, because for some reason, when I looked at this, I interpreted it backwards. But I think now, I think we actually got what we wanted, right? We are seeking the natural frequency being significantly higher than the fan frequency. And that's precisely what happened. Wow. Okay. I feel much better about this. I was about to tell you guys that I did all this work and this thing didn't work, but this actually works out okay now. Oh my God. Okay. So I'm gonna cross this out. Bing. And found it. Yay. And we can get rid of Macaulay Culkin.
So earlier when you said that it needed to be much higher so that when we added in the other 3 attachment points, it would still not like be within the range. How do we know what's much higher to the point where adding 3 attachment points doesn't bring it within the range? Because 500 to about 100 or 600 to about 100, that seems a lot higher, but we don't really know what an extra attachment point does to the natural frequency. Do we? I mean, I don't know.
Yeah, no, I don't know either. So let's go back to this original equation here. So I think okay. I think I've been thinking about it backwards. Um so my initial thought was with one attachment point, we get this K value that we calculated before, right? So that's what this is. And if I've got 4 attachment points, K should get stiffer, right? Which means that the K value should be higher. Let's see, does that make sense? Yeah, that makes sense, because here, let me grab my annotation tool. This is good. I'm glad that I'm glad that I messed up, because it gives us a chance to really sort of think through this and talk about it in a more sophisticated way. So if the spring constant is higher, that would be, like a slope like that, right? Would be higher. And does that make intuitive sense? It does, because if I go all the way back to my original experiment, right, which is, I've got a picture of it here, maybe, there we go. The stiffer the spring, what that means is for some force, right? So let's just look at let's look at one like 3, right? So for some force like 3 newtons, if I'm stiffer, I get less displacement, right? So hence the purple line as opposed to the blue line. So that's okay. And so then if I go here and K gets bigger, then my natural frequency ends up being even higher than what I had before, which is this about 600 hertz. And so then if I go here, this is like a lower bound on the natural frequency of the system, even if it's got 4 attachment points, right? Do you agree with that statement at least?
Yeah, that makes sense. We were just talking
Okay.
about it all backwards the whole time, so
Yeah.
this makes sense.
Sorry. Yeah. No, yeah. And I realized now I've been like, oh my God, I just realized I did it all backwards. Yeah. Okay. So, because, yeah. So this is what I was expecting to get. And then I got to the very end and I got this and I'm like, oh no, it's less. And I didn't interpret it correctly. So this is a lower bound on the natural frequency. If I add additional attachment points, K goes up, which causes the natural frequency to go up as a result of this relationship. And so I actually got what I wanted. So hence I can get rid of Macaulay Culkin, which is, yes, in fact, the natural frequency, which I calculated, and that's a lower bound on what that value is higher than the frequency at which this fan spins at 12 volts, right? Which is also, by the way, an upper bound on that frequency, because the fan spins more slowly with less power input, lower voltage input, but it never spins faster than this, right? I mean, it can, you can overclock it, but you don't want to, right? Because if you put more than 12 volts into the fan, okay, yes, it'll spin faster, you get more cooling, but then the fan dies quite a bit faster, because the voltage jumps over the windings inside of it, and so it ends up frying it electrically if you overclock it by going more than 12 volts. So this is also an upper bound on the natural frequency of the fan. And so never, this is great actually. Okay, I feel so much better about this. Okay. So the natural frequency, or the highest frequency that the fan ever achieves, is this 91 hertz, right? Associated with this 5,455 RPM. That's an upper bound there. And 600 hertz is the lower bound on the natural frequency of the heatsink. So, okay, yeah. So, wow, I've come full circle. Now I'm back. So, never does the fan reach a rotation rate that, if there was a mass imbalance, that rotation rate would induce a forcing function that has a frequency anywhere near the natural frequency of the heatsink. So So it actually worked. Wow. Okay. I was all like depressed because when I started to do this analysis, I thought that this was going to work, and then I interpreted it backwards, um, and I thought it didn't work, but it actually does. Okay, cool. So let me just take a quick pause there because this was a lot of like, flip flopping back and forth and reversing, and let me just make sure that are you guys, is everyone following? You guys have questions about kind of the bad path that I went down and got myself back to a good place? Everyone okay with where we are?
Makes sense to me.
Okay, great. Wow. Okay. This actually worked out a lot better than I had imagined when I started class, because I'd thought that it was going to be the reverse. So okay, so this is great. So we've got a because let's just imagine, because I was I had in my head that, like, what am I going to tell these guys if we get to the end and it doesn't work out? How am I going to explain this to them? Because if you're the designer of this thing, right, having a situation where this is reversed, right, where the natural frequency is lower than the frequency created by the spinning of the fan, is a really bad situation any way you cut it, because you could potentially, if these two numbers almost match each other, then you could get into a situation where you've got this vibration amplification, which, as we know from the Mech 1 analysis, ruins the lifetime of the fan, of the heat sink. But then there's also the problem, or the possibility, there's two other possible failure modes. One is, even if these two numbers ultimately don't match, if F1 is less than F fan, that means that the fan still has to spin through the natural frequency to get to its steady state rotation rate, right? And I don't know if you guys ever saw any like videos or anything of people trying to push dynamic systems through a natural frequency, but they go bonkers, right? They vibrate and shake, and it's a very horrible, scary situation. And so the designer of this thing is sort of taking a risk, right? If provided it worked out the other way, that as the fan spins up, it actually has to travel through a natural frequency, and potentially cause damage to the heatsink. The other possible badness, is if you're running the fan at less than 12 volts, it's going to spin slower, right? So again, if F1 were less than F fan, which it's not, but if it were, you might end up in a situation where somebody has taken out their heat sink and put in the heat sink that you've just sold them, which is this one that we're reverse engineering, not realizing that it's got this sort of natural frequency problem, and you might not need 12 volts to run it at the speed that you want. So you might run it at 9 volts or 8 volts or something like that to get a lower rotation rate. And you might accidentally, inadvertently run it at at its natural frequency, which would cause your entire computer to probably explode, as a result of this vibration amplification. So there's actually two different possible dangers, if this number is less than that number. And I was just trying to think to myself, like, how can I possibly explain that design decision? And I was going to say, like, before I erased Macaulay Culkin, I was going to say, okay, if it worked out that F1 was less than F fan, then we have to, of course, go to one of these more sophisticated analyses here. Let me get rid of this line that I've got across my, it's now in the way. Boom. Okay. So we might have to go to one of these more sophisticated, modeling type analyses to check to see whether or not, this number that I got is actually, correct or in the ballpark. And so that's what I was going to say is, oh, this gives you motivation to go and, do these other things now. So go do them. But now we don't have to, because the calculation actually worked out the way that I wanted it to, the way that I hoped it would, which it did, which is amazing. And this then gives us sort of a glimpse into the mind of the designer, right? So why are the fins the way they are? Like, for example, right? Like, why, if we go back to, why is this thick cantilever thick fin. Why is it thicker than all the other ones, right? That seems, sort of annoying. Those of you guys that have the older fans, you probably noticed that all of or the older heat sinks, you've noticed that all of those heat sinks, all the fins are the same, right? They're all the same width, at least in some of them. And in a lot of cases, there's an extra part that's this like plastic piece that gets stuck on the top here, that serves as kind of the mounting location for the fan. And so this is amazing. This all ties in together. So think about like from a design for manufacturing or design from assembly analysis from DML, right? You want to reduce the part count as much as possible, and you don't want to have to manufacture that extra piece that sits on the top here that allows you to mount the fan to the heatsink. And so what did they do, right? They went through a DFMA process where they eliminated that piece, and then they said to themselves, okay, what problems are going to be created? What failure modes are we accidentally, inadvertently going to set up by doing that? And I bet you one of those failure modes was the one that we're talking about, right? This idea that the natural frequency of these thinner fins, right? Because what happens, right? The natural frequency of a thinner fin, you guys can calculate it, it's less thick, and so it's less stiff, so the K value is less, and so the natural frequency is going to be lower. And I don't know how much lower. You guys can do that calculation. That would actually be super interesting to do. But if it's like half of this, something like that, we're at 300 hertz, maybe 250 hertz, who knows, you're all of a sudden getting awfully close to this value, right? You're still off by a bit, but you want to be as far away from this frequency as you can possibly get, and above it, right? As far away and above it as you can possibly get, to avoid this vibration amplification issue that happens when you get in and around the natural frequency, or any harmonic of it. That's the other thing. Any harmonic, you want to avoid those too. So I bet you that's exactly why these are thicker than these fins. Is one, you've got enough room there now to mount those screws, right? So that's beneficial. But then two, your natural frequency is so far away from the frequency associated with the spinning of the fan that there's no worry that you're ever going to hit a natural frequency or its harmonic. So wow, okay, that's amazing. I feel so much better about this analysis now that it worked out the way that I wanted it to. So anyway, so you can sort of get a glimpse into the mind of the designer, and why they're mounting the fans on the thicker fins, why the fins have to be thicker, to begin with, both from the perspective of DML, right, which is the design for manufacturing and assembly analysis, reducing part count, and from the dynamics analysis standpoint of, I want to stay way, 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 way far away from a natural frequency when I mount the fan directly to this part, which is basically just a cantilevered spring. So, wow. Okay. That's really cool. I learned something today just by going through this analysis. So, okay, let me, that's it. That's all I've got for today. So let me just pause there, and ask if anyone has questions. There was one question in the chat, about the template. So I'll get to that in just 1 second, but let me just make sure there's no questions about this analysis that I did and kind of my interpretation of it.